So my name is Trenton Holyfield, and along with me is in this group is Tim Dyer and Vanessa Marcello. And through our group members' experience and combined interest, we tasked ourselves with conducting a multi-beam scan of the Cedarville shipwreck in the Mackinac Straits. So hydrographic surveying is more common amongst coastal areas, and there are also lots of applications that can be applied to the Great Lakes. So for those who need a brief description on hydrographic surveying, it is the science of measuring all factors beneath the water that affect all marine activities. And some of the measurable things can be depth, shorelines, tides, currents, submerged obstructions, such as in our project. A little bit on the applications of hydrography. Bathymetric mapping involves multi-beam, which measures an entire area with a swath, as opposed to a single beam, which measures a single depth. In our project, we used multi-beam scanning. Dredging is usually done to meet specific grade standards through shipping channels, which is very common in the Great Lakes. And object detection, such as in our project, can be done to locate underwater obstructions.
So we wanted to touch on what our plan was during this process of our capstone. And our first step was coming up with the idea. And we all agreed that we were interested in hydrographic surveying. And with that, we decided to scan a shipwreck. From there, we had to do some research. We had to find local or even possible shipwrecks just to make sure we can follow through with this idea. During our research, we came in contact with the Michigan Shipwreck Research Association, and we told them about our idea, and they liked it and they wanted to help us with it, but they ended up being a diving-based association and they lacked the hydrographic equipment that we desired, so we decided that we weren't going to go through with them. From there, Tim ended up working with eTrack during the summer of 2019, and they are based in California, but they were working in Michigan. They were mapping the Straits of Mackinac for the purpose of updating navigational charts. And we proposed our idea to them, and they were more than enthusiastic about it, and they committed to assisting us with this project. And after following through with eTrack, we had to pick a shipwreck. While working with eTrack, the logistics were the most important thing. We had to work around their work schedule while they were mapping the Straits of Mackinac, and at this time we have gone back to school, so we were working around our class schedule. And most importantly, we had to work around the weather, because if the weather was bad, there was no way we would be able to go out and scan the shipwreck. The first day of the data collection, we planned to be in Mackinac, and this would be scanning the shipwreck. We had to make sure that eTrack had a vessel available for us during this day, so they picked a maintenance day. On the vessel, we had to make sure that they had positioning equipment, sonar equipment, the platform itself, and data acquisitioning software, so we could make sure that we would be able to collect all the data that we needed. The second day, we planned to be in Charlevoix, and this day we planned to scan the vessel that we were using. And the vessel had to be completely pulled out of the water for us to get a full scan. And we used the Trimble SX10 and the tablet, but we were restricted to a very small amount of time that we could actually scan the vessel that day. So before we left, we scanned Tim's truck, just to make sure that we knew how to use the SX10 and that we were doing everything correctly, just to make sure we had enough time to get the scan completely done while in Charlevoix. After all the data was collected, we had to plan for the processing of that data, and with that we had to use the Trimble Business Center, Trimble Railworks, QPS, more specifically Cumera, and Mesh Lab, and we planned to 3D print the shipwreck and the vessel, so we were going to use a 3D printer.
Okay, I'm going to talk about the equipment that makes up a hydrographic surveying system, which includes a platform. And for our platform, it was a vessel. We used a multi-beam sonar and positioning equipment, which is GNSS and an IMU integrated together. We also needed to have a scanner for the full vessel survey to get the parameters, and software also for the data acquisition. So this image here is the RV Endeavor. It has a catamaran hull, which is requires minimum draft, so it keeps the a lot of the boat the hull not deep in water, so you can go in shallow areas. Has a large fuel capacity for long surveys, or if they're far out, which for us, the shipwreck was very convenient. It was right outside the harbor here in Mackinac. And also the vessel's large, being a 44-foot vessel, you can conduct surveys in pretty rough weather and not have too much effect on the data. This image here is the R2 Sonic 2024 multi-beam sonar. We have a dual head system here, so there's actually two sonars there, one on the left, one on the right, and they overlap. So that ensures that there's plenty of sounding density traveling at speed. The range of frequency goes from 170 kilohertz to 450 kilohertz. That's important because depends on what the bottom of the lake or the ocean, whatever you're surveying, is made up of. So if you are trying to find hard bottom and there's lots of silt on the bottom of the lake, then you need to use a lower frequency so that it's more powerful and it will go through the silt and hit the hard bottoms. But the problem with a lower frequency is a lower resolution, so you're not catching a lot of detail. Small details. So using a high frequency for maybe a shallower project would be better for that. It shoots out 256 beams, and those can be directed in a swath formation. So it's like a sector, and the sector can go from 10 degrees to 160 degrees. And that just means that you could spread the beams out really wide if you wanted a lot of coverage, but your sounding densities will be lower. If you were to bring the sectors in really close together, then you'll see a lot higher density, sounding densities. For the positioning hardware that we had, that the RV Endeavor was equipped with, was the Aplenex Pause MV, which is a GNSS and IMU integrated system. The GNSS antennas were Trimble antennas. They took care of the geographic position of the vessel, and the IMU takes care of all the motion of the platform. Because it's in the water, it's rolling around, and all those angles change when you're sending down the soundings, and that can affect where positions are and depths. So the IMU measures all those motions, the heading, the attitude, which is the rolling pitch, heave, the velocity of the vessel, acceleration, and the angular rate of turn. the way it was installed onto the vessel, you can see at the roof of the Endeavor, there's two small antennas. Those are the trim antennas. They create a baseline on the vessel for its own reference system. And then those parameters will be measured from the antennas to the IMU. It's important to keep the antennas away from any other structures on the vessel or any other signaling like radar devices, so that there's less cycle slip or any other the IMU was installed onto the actual sonar head, which is, you can see in this picture on the right, is attached to a lever arm, which hangs over the side of the vessel. And then that is dragged along the vessel. The reason that the IMU is on the sonar head, maybe not on the vessel, is because even that lever arm will wiggle as the vessel travels in the water. And we want to account for all motions. Here's a little diagram of how it works. You have the two antennas, which you'll have a measurement between those two, and then you'll have a measurement to the IMU, which this system creates good geometry, especially when you're having satellites too, having two GNSS antennas. And it's just to make sure that you have tightest measurements possible. And being in the Great Lakes, we were able to also tie into the RTK network, which a lot of other projects, if you're out in the ocean, since Michigan is such a robust system, we were able to use that data as well.
Okay, so just for a little background information on the shipwreck, we chose the Cedarville shipwreck. It was built in 1927 and sank May 7th of 1965. The reason behind this is due to thick fog and lack of communication with other ships. The purpose of the Cedarville ship was for the transportation of limestone, and on this day it was carrying just over 14,000 tons of limestone, and it had a crew of 35. It collided with a Norwegian vessel on its port side, and that's why it sank. The size of the Cedarville ship is 604 feet by 60 feet by 32 feet. And where it sits now in Lake Huron, it's at a varying depth between 40 feet and 110 feet.
Marissa, you cannot be a speaker and then hide behind the screen unless you are having bad hair day. You should turn that video on.
My webcam actually isn't working, and we tried to fix it before the presentation, but we couldn't.
Oh, I'm sorry, I didn't know that.
It's okay. Anyways, the first day of our data collection, we were in Mackinac, and this was September 11th of 2019. Before we could leave the dock to go to the shipwreck, we had to start the pause MV, which is GNSS being integrated with IMU, and that allows for the tracking of the motion of the vessel. And the pause MV checks for the accuracies, which include attitude, heading, position, velocity, and heave. And in this image, you can see under the accuracy, they all checked, so we were able to leave the dock. When we arrived at the site, we had to perform a sound velocity cast, and it was performed with the profiler as shown in the images. The profiler checks, or it will measure the temperature of the water, the pressure of the water, and the turbidity, so like how clear the water is. We used QPS, which is a quality position service, during our survey, and more specifically, we were using Quincy. which is the Quality Integrated Navigation System. This is the software that we are using on the vessel while performing our survey. The sound velocity cast will create a profile, and that profile is applied to the Quincy software, and it will calculate the refraction corrections. And this image shows what the profile looks like. And as you can see, as the depth increased, so did the velocity. Along with the profiler, there is a probe attached to the head of the sonar. And the purpose of this probe is to confirm the real-time water conditions and make sure that they match the conditions that were recorded from the sound velocity profile. This image to the right shows the alerts, and since all the alerts are green, this means that we were able to continue with our survey.
So this display here is showing the sonars, the left sonar and right sonar of the dual head system. Here you can adjust all the settings, and settings of the sonar are determined by the underwater environment. So that also includes the turbidity and things that the sound profiler measured. Here you can adjust the sector, which is how wide the swath is and how much, depending on how much density, sounding density you want in an area. You can also adjust the range, and that's what the sonar is expecting to receive a depth or a sounding depth. So that will adjust the amplitude, basically, how powerful the sound has to project to get a good sounding back. So you have to set that, you'll see the bottom, and then you have to adjust it to make sure that it's getting clean sound. Also here you can adjust which frequency you're using. You can adjust the gain, which is also kind of is with the power and the range, and the pulse width. Pulse width is how long the sounding goes for. So like how long like a beat would be. This is the Quincy program here, their planning program. We made a data grid, a grid over the wreck where the captain of the vessel would be able to follow these lines, or you can set the autopilot to it. And it was basically to make sure that we get 100% coverage of the wreck. We knew where the beginning and end of it was, so we knew how close we needed to set the lines, and this makes it efficient coverage. This display here is after we completed the passes over the wreck, and this is millions of points. It's all raw data. You'll see there's a lot of noise around the sides of the vessel because those are hard angles of the vessel, and you're getting lots of scattering from the sound waves. So it's not really going to be clear data, and that's what we'll take care of later in the post process.
So we scanned the survey vessel in order to more accurately calculate offset parameters as opposed to doing it with a tape, which is what eTrack does. So we did this so that we could compare our results with theirs. The offset parameters included IMU to antenna heights and sonar head to antenna heights. The purpose of this is similar to measuring an HI to get accurate elevations when conducting the topo. And we used a Trimble SX10 single beam scanner provided by Seiler. It took 6 setups to get the desired overlap and point density. On the data collector, we chose a fine point density option. And we could have done a finer option, but the scan times would have been overkill for what we needed. Um, 6 scans called for 6 ground control points around the vessel, as you can see in the picture. We strategically placed stick-on targets on the hull of the boat. And the target stickers were placed so at least one target would be represented in each of the 6 scans. The targets were used for cross-referencing scans so they can be accurately stitched together. And we backsighted a Trimble 360 prism to establish position with our local coordinate system. A local coordinate system was used because we weren't concerned with our geographic location, but rather coordinates relative within themselves. And these are some of this is one of the models we created with Trimble RealWorks. And go to the next, yep. So using the measurement tool, I talked about the offset parameters. We were able to measure our offset parameters with the measuring tool and compare them to the taped measurements given to us by eTrack.
Okay, so now that all of our field data was complete, now we're into the post-processing of the data we collected. For that, we used a program called Chimera. It's another program made by QPS. So first, we had to bring in raw data files. The raw files are full of the noise from the sonar data and also noise from the GNSS data, the position data. So first, to make sure that we had the best matching of the files, because of all the different passes, which was its own file, to make sure that it was all matching together, we had to adjust the positioning data. To do that, we had to apply an SBET, which is a smooth best estimate of trajectory. I'll show you here. So this is an image of the raw data tracks of what the vessel actually, or what the vessel thought it was traveling. After we applied the smooth best estimate of trajectory, SBET, you can see the white line is what it adjusted for. So it takes the IMU data and the GNSS data and averages them to where that they where the vessel actually was passing, or actually would be where the sonar head was actually crossing over. In the program, they show you what the estimated errors of data was. So this is the GNSS data. It ranges from 10 to 12 centimeters of error. You can see it spiking from different reasons, whether it's obstructions or cycle slip or however. After you apply the SBET, average it all out, and it brings it down to below 500s. This image here is now is the sonar data. Now we're going to take all the uncertainties on the sonar data. So here you can see these green along the data, along the ship. I had the color scheme set so that you can see that there's a lot of different depths in one small area. So you're getting lots of different readings, and the software basically alerts you saying that, this one of these is not correct. So there's millions of points, and you have to go through and you have to clean all these out, and by just making judgment when you bring it into the 3D slice editor. This is the image of the slice editor. You can take a selection of points and you can rotate this 360 degrees, and you can see where, like, if there's any scattering above the vessel or if you're getting false soundings below the ground. Some of those errors come from the motion of the vessel and and the turbidity in the water. So you have to go through it manually, slice by slice, and clean all of the bad data out. Once you're done, you'll have a much better estimation of the actual depth of the ground and air obstruction for the shipwreck. Once we cleaned all the data, we wanted to make our 3D print of the shipwreck. So we had to figure out how to get all those data points, the point cloud, into software and turn it into a mesh, and then get it into the printer software. So to do that, we had to export our QPDs, which is what Quincy uses, and turn them into a .xyz file. That was kind of difficult at first to get the hang of moving all these data points. But once we did, we got into MeshLab, which is a open source software for manipulating point clouds and turning them into meshes that can be read by the printers. So important things I learned on in creating this mesh was an object has to be manifold. And manifold means that there can't be any holes in the data. So it needs to be a complete, solid, watertight hole. When you get with the point cloud of the shipwreck, it is not a solid image because you can't get underneath the vessel. You can't get some of the things that, like if there's any overhanging bits of the ship, then you don't, it creates a shadow on the ground, so you don't have any of those points. So you have to go through and run filters and create faces in the software. And then running filters, and you can try to reconstruct the surface and try to create the mesh. And I had a lot of trouble with it because of all the once you're done, you have to export it to a .stl. That's what
All right, so when considering your deliverables, you should ask yourself what the purpose of the survey was before deciding what type of model to create. For our purpose, it was just to preserve a historical artifact. And we created these models represented on the slide and plan to create a physical 3D model through 3D printing until obviously we were hit with the roadblock with the COVID-19. We did create a 3D digital model represented in the picture of the vessel in both Trimble Business Center and Trimble RealWorks. And some of our cost estimates, our travel, $2,000 for the vessel. Crew was $1,000 for an 8-hour day. The equipment rental was $5,000, and time of processing was $900, which gave us our total of $8,900. Some issues we encountered with data. Some of our file sizes were too large, which led us to sometimes we would download some of our data overnight and then come back and deal with whatever issues we had with that. That could have been the reason for that could have been our free trials may not have been able to handle the data, or it could have just been the computer software we were working with. We had a big learning curve with getting the QPDs, which is the Quincy data, into XYZ file so that we could then get that into MeshLab and create the 3D model. And our licenses expired, and I think Tim did get to renew some of them, but yeah, ultimately, I think before the school year, they did expire. And then obviously the COVID was a big roadblock for us with finishing up some things we wanted. And our acknowledgements, David Neff from eTrack. eTrack was a huge help with providing basically all the software and conducting the survey, the vessel. Seiler for letting us use the scanners and equipment from Ferris. Matthew Wilson, I think is the guy we dealt with for the free QPS subscription. And Ferris surveying professors with their support. So I think that is it.